department. So if any of the lectures on this course are rubbish, you've got to tell me and I'll fire them. And also, yeah, I guess that's all I need to say. Over to Colin.
Yeah, and I suppose some of you might not have been taught by me. I'm Conor McBride. I'm deputy head of department, so if my lectures are rubbish, he can fire me. I guess, well, we've got the 1-minute papers going around. They're, if you've seen this system before, they are an opportunity. They're an attendance mechanism, so please do fill one in, but they're also an opportunity to indicate things which are making sense to you, and more importantly, things which are not making sense to you. So I suppose we should try and make some sense.
It's always an idea.
You're on first.
Right.
So,
Okay, so first thing I'm going to do is take my jacket off. So, I'm going to tell you about the objectives for this class. So there are 3 objectives on the website for the class. Oh, let me tell you about the website for the class.
Owing to a minor technical mishap, neither of us currently has the privilege to edit the MyPlace resources for this class, which is a bit of a pain in the bum. But we're getting that fixed as quickly as possible. Inevitably, of course, we're not actually going to put anything on MyPlace except for a link to the real website, and that does exist. In fact, while Neil talks, I'll connect a computer up,
Okay.
and the website will appear behind him.
Right. So, in dynamic activity, you're about to see the website, and the website, the first thing it does is talks about the objectives of this class. So what we want to do is tell you about programming languages. You've used programming languages, we've taught you programming languages. I think you've learned some Java, maybe some web scripting languages, some PHP, maybe some Python, maybe some Haskell. So you've used quite a few. And by this stage you're realizing, God, there's a lot of them. But what you've not really done is figured out how they work. So, you know, if you're going to write your own programming languages, and that's an interesting thing to do, and that's a valuable thing to do, what do you need to do? If you like, that's the point about this class. It's how to understand how programming languages work, and how to therefore be able to write your own. If you know how to write your own programming language, you pass this class. So in doing so, there's a number of different objectives. The first thing to understand is, you know, when you see a program, either you've written it or somebody else has written it, what's it going to do? Well, you might have an idea what it's going to do, especially if you've written it. I mean, I hope you've got an idea about what it's going to do. But what actually happens? So we're going to tell you about that. So that's what's called comprehension. Oh, here we go. Comprehension. When you read a program, you know, you've got an idea, that's your model, but what's going to actually happen when you run it? So in order to do that, you'll have to understand the actual programming language, how the programming language works. What does the computer do to the program that you've written? And so for that, we're going to talk about what programming languages are, how they are fit for purpose. You know, all programming languages have to do various different things. How well do they do them? They all make choices. There is no one universal programming language. I guess, you know, when we meet our first programming language, we think that is the language. You know, everything else is much the same. It's basically just this language. But as you learn more and more programming languages, you realize they're fundamentally different. Different languages for different purposes. So what are the choices that they've made? That's what we're going to teach you about here. Oh, that's gone. Yeah. So, under what's it? Comprehension. Under critical thinking, you'll be able to look at a programming language and say, oh, I see. It needs to discharge this. It's doing it in that way. It needs to do this. It's doing it in that way. So all the common things that all programming languages have to do, choices are made in individual languages. And then the third objective is, well, if you understand, you know, what the things that programming languages have to do are, well, in different areas, you might want to write your own programming language. So some programming languages are universal, like Java, you know, you just use them in general for all sorts of different things. But if you're working in a specific area, you don't want a general purpose language. You want a specific language that does what you need to do. It's got special built-in primitives to do all the things that are important to your domain. So these are called domain-specific languages, and we're going to teach you about them. Okay, that's my bit.
Yeah, so I pulled up this XKCD cartoon because it's actually my life. My father was a programming language implementer. He specialized in versions.
I'm glad you said implementer.
Of Lisp, which is a language that has lots of parentheses in it. And I picked up his toys when I was little, and that's how I became the person I am. So yeah, this really happened to me. So we're so glad we're teaching this class because it's what we actually do for a living in various ways. This is programming languages, definition and implementation. And Neil is an expert in the definition of programming languages, in the tools that allow you to say what programs mean. And whilst I wouldn't characterize myself as an expert, I at least have a habit of implementing programming languages, as some of you.
You may have heard the modesty klaxon going there.
Okay, I suppose I should do the usual administrivia. Let's see, where did I hide that website? It was one of these ones. Ah, it's this one, right. So the URL is too small to read because I'm plugged in with HDMI, but I'll send a message around. I've got a website for this class built on the same server that I use for CS106. It is, of course, under construction, but that's where this class will live. And I guess what else? So I will, as soon as I get access to the My Place page for this class, I will put a link to this site on it. And hopefully that way you'll find it. I'll also do the old-fashioned thing of sending around an email. Would that work? All right. Okay. Okay, let's do lectures. So that's now. So Tuesdays at noon here in this wonderful room that means you can't see all the people all the time because pillars in the wrong place. And on Thursdays at 11 we have the much lovelier McCants 303. On Thursday mornings, we also have a lab session at the joy of 9 a.m. Woohoo. And then something weird happens at 10 a.m. So Thursday morning is CS311 morning from 9 until noon. It starts with an hour that is definitely in the lab, and it finishes with an hour that's definitely in McCants 303. But in the middle, we actually have both booked, starting from week 3. We've only got the lab in weeks 1 and 2. So that will either be more lab or a tutorial session rather than a 2-hour lecture. But that will either be a lab in level 12 of Livy Tower or a tutorial also in McCants 303. I promise you, if we're doing 2 hours in McCants 303, there will definitely be a half-time break. Not least because I need a cigarette. But so
I'll have one whether I need one or not.
Yeah. Yeah. So we got this week. Actually, for the first 3 weeks of term, we're doing a 2-hour lab in Livy Tower level 12. Now, it occurs to me that there might be too many of us. If you have your own equipment, it might be sensible in the first instance to bring it. If we're too big for that lab space, then I'll try and get more allocated. It's one of these things where class sizes, a few weeks ago there were 60 people registered for this class and that would fit in those labs, and then more people arrived after the timetable had already appeared. So we might need to keep an eye on that. Okay, but the crucial question is what the hell you have to do to pass the class. So let's get there. This class is on the books as 30% coursework, 70% exam. And because the score for this class counts towards your final degree classification, like all third-year classes do, we can't fool about with some people doing exams and some people getting exemptions, I'm afraid. The method by which we arrive at a score has to be uniform, and that means we're not allowed to run an exemption scheme, for which I can only apologize. So everyone does the exam at the end of semester, and that will be an exciting 2 hours in an exam room somewhere. Is this anybody? Will that be anybody's like first ever paper exam at this university? Maybe. Anyway, that's the deal we've inherited, and we are not in a position to change it just now. The 30% coursework is going to consist of 4 assignments, and our current plan is that these will be due on the Mondays of weeks 3, 6, 8, and 11. We got a fun plan designed to encourage peer-assisted learning. The idea is that each assignment will have a homework phase and a test phase. So you start off on the homework phase, you get 2 or 3 weeks to do a task, and you do it in groups of 3. And we'll be making a group assignment later this week. So groups of 3, hopefully collaborating and figuring out what's going on. You hand in your homework on the Monday, and then in the lab session the following Thursday, you do the second phase of the assignment individually. And this is just to sort of generate appropriate evidence that you have individually learned something from the experience. Generally speaking, phase 2 assignments, they'll not be wildly different from what was going on in phase 1. If your group has collectively cracked phase 1 of the assignment, then individually you should find phase 2 no bother. The obvious thing that we're trying to deal with, might as well be transparent about it, is that we're trying to address one of the difficulties with group work, which is that people sometimes zone out, leave the others to do the work, and collect the credit anyway. The phase 2 mechanism is partly in place to ensure that if you as an individual don't get the message of what your group has constructed, then that will bite you. Okay? So work together in groups and make sure everybody in your group is along for the ride. is the message. So in particular, we're going to have a lab exercise on Thursday, which is mostly a bit of fun. It doesn't count towards your score for this class. Its purpose is twofold. We're just going to explore, it's going to be like an online multiple choice or not very complicated quiz. And we're just going to explore what you currently know and what gaps there are in your knowledge, so that we know where to start from in terms of pitching material to you. And we're also going to use the results of that quiz to do the assignment of groups. So I'm afraid to say, sorry, you don't just get to pal up with your mates. We will construct a group assignment off the back of the results of Thursday's quiz. So that's the plan. 4 assignments, they're each worth a quarter. That will contribute 30% towards your overall score. And then there'll be a 2-hour paper exam at the end of the semester, which is your other 70%. Okay, everyone happy with that as the mechanism?
I have a question.
Yeah.
So I remember we worked out when we'd give feedback or when we'd return the assignment, so we didn't put it on here. We will put it on here, but do you remember when we will give the feedback?
Well, the plan is that the Thursday after, so there's phase 2 happens on a Thursday in a lab, and then the following Thursday we'll have a tutorial where we will give you collective feedback, but I hope by then you will also have had, if we can turn the marking around in a week, it would make more sense if you got the individual feedback before we did the kind of tutorial review of the exercise. So that's the plan. Okay, I guess we should actually talk about like what class is about.
Mm-hmm. Okay. So using them. Click. Oh no!
Just click there.
Right. Okay. So this is, if you like, the first lecture. So what's the class about? So on the class homepage, there's something about objectives, which I spoke about a few minutes ago. So what does that mean for an actual programming language? So this is the general stuff that you need to understand about any programming language. All programming languages need to do something like these 1, 2, 3, 4 things. So I'll give you 4 things that we're going to tell you about programming languages, and they all have to do that in somehow. They might do other things as well, and they might do them in different ways, but all the different languages we speak about are going to have to talk about 4 things. So the first one is the syntax of the language. When you type a program in, you could type gobbledygook. You could type question mark X, exclamation mark 5. Now, that's not a program. But other things, you could type while X is greater than 5, do X equals X minus 1, something like that. That may well be a program. Sounds like a program, may well be a program. So, any programming language, when you type something in, the language is going to have to say, is this an actual program or not? So that's what the syntax is about. So as it says, when you write programs as text, how do you tell the difference between text, which might be programs, like a while loop, from any old nonsense, like the one I started with? So that's the first thing that has to happen. So what the computer is going to do is what's called parsing. It's going to take the string, which is a sequence of characters, and match it against what's called a grammar. So what makes an actual program isn't that it's a correct string. Strings are not really very interesting structured data structures. The actual definition of what a program is given by what's called a grammar. And so program, the programming language, is going to have to say which of the translate these strings into the grammar. If it succeeds, it's a well-formed program. If it doesn't, if it can't find a grammatical match, then it says no, this is just nonsense. And so what happens? So the result is a syntax tree. So if you like, the syntax tree is the abstract representation of the program. The concrete representation might be a string. It's not a very interesting one for reasons we'll cover later. What you really want to know is the syntax tree. And so that's what parsing does. Is there anything else to say here? Right, so we'll be talking about languages, what their grammars look like, how parsing works, and what the syntax trees consist for them. Some of the difficulties and limitations, and some quotes missing here, and whatever else is needed. So that's the first thing, the syntax. When is a string an actual program, i.e. when can it be parsed into a syntax tree?
Yes, because in particular, ampersand ls quote semicolon does not parse as a valid HTML entity.
So in fact, indeed, there's a programming language behind this, and as we spotted, this is not a valid string for that programming language. We've tried to deal with it. It says, what are you talking about? This is garbage. And it spat out some garbage in return for us. So we now have to go back and think, why is this not proper syntax? What is the syntax of HTML? Why have we not met that? When we figure that out, we'll change our typing string, and then hopefully something nice and pretty will occur here.
Okay, I think I'm up next. So yeah, next thing, we'll be talking about the dynamic semantics of programs. Maybe I'll go over here and talk about the dynamic semantics of programs with the camera pointing at me. So right, programs don't just sit there looking cute. They're supposed to go, right? You want them to do stuff when you run them. You don't just say, oh, that's a beautiful program, and frame it and put it on the wall. Once you've got past the is this a program at all stage, you need to be able to make it go, to explain what the different constructs of the programming language mean in terms of what they're supposed to do when you use them. So how programs run, what they mean in terms of computational activity is known as the dynamic semantics of programs. So dynamic as in about activity, about going, semantics as in meaning. When you write a program in, I don't know, the lambda calculus, if you remember the lambda calculus from last year, then how do programs in the lambda calculus go? They go by doing beta reduction. And similarly, when we have any programming language, we have to say how programs go. So we'd be looking at systematic ways to specify what programs are supposed to do when we run them at a high level, right? It's one thing. So how do we build an intuitive understanding of what a program is going to do? At this stage, you ought to be able to look at a program that's written in a programming language and think, well, I know how this programming language goes, so I've got a model in my head of what that program will do when I run it. What would be making sense there? We also had to think about how programming languages stop. I mean, when is the execution of a program finished? Essentially, when the answer comes out, right? So we have to think about, well, how do we characterize the ways of stopping? What constitutes reaching a value or reaching the end? So we'll be thinking about, how to characterize the machinery where, program comes in, churns away for a while, value comes out. And we'll be thinking about that in lots of different ways, because there's lots of different ways to do it, right? One way to do it is to talk about how the program makes a series of small steps, what a small step of execution would be, and then we have to characterize what finished looks like. And finished might just be, isn't able to make another step. We can also characterize the behavior of programs all in one go. We just say, here are the conditions for this program delivering this final state. And we can characterize, we can work in that sort of way as well. So this is about building a way to talk about what, in principle, the constructs of a programming language are supposed to do. That's called specifying the dynamic semantics. But it is also the case that not everything that fits the grammar of a programming language is necessarily a sensible thing, right? So in particular, well, why don't I just Google it? Yeah, so that's what static semantics is about. Neil, why don't you do some static semantics?
I will do. Are you going to help me?
Yeah,
okay.
I'm going to Google the new Kayama sign.
Well, while we do that, I forgot to introduce one of our helpers. So this is, what's your name again? Stuart. This is Stuart. So he's helping us give the course. So he's going to be in the labs. So he'll be your friend, and you can ask him lots of questions as well.
Ben as well.
And there's also Ben, but Ben's not here. You, Ben? Here, Ben? Any Bens?
No, Ben's not here.
No, Ben's not here. Okay. So we'll have 2 demonstrators helping in the lab. So that's what you get from having a head and a deputy head taking the class. You get lots of demonstrators to help you as well. Okay. Thank you. That's all I wanted to share. So, right, yes. So what Connor said, what I started off by saying was, when you write a program, is it a valid program? That's what the syntax is. The syntax says, these strings are okay. Those things are garbage, but these are okay. And what Connor said was, okay, when you've got your okay program, you press the button, you press run, and you hope you get your number out or something. But sometimes that doesn't happen. And all sorts of things can go wrong. Somewhere in the middle of your program, you could be trying to divide by 0. Somewhere you could be trying to access a variable which hasn't got a value. Sometimes you might be trying to add things. And, oh no, one of the things you're adding is a number, but the other one's a string. So all sorts of things can go wrong. And rather than leaving it to you to press the run button and find out, instead of getting your lovely number that you hope for, you just get an error or an infinite loop or something like that, static semantics tries to get in there before the dynamic semantics, and it tries to do a little bit of understanding. See, is this program, it's a well-formed program, the syntax is right, but is it really going to give us a number? Is it really going to run and give us a value at the end? Now, we can't be perfect, ultimately, you have to run it to see if it's going to work. But there's lots of different things we can do. And that's what dynamic semantics is. It's like saying, oh, sorry, that's what static semantics is. It's static because you're not running it. When I talked about dynamic semantics, what happens when you run your program to get your values? There's a static semantics, you're not running it, you just say, oh, I've used the plus symbol. That means you two must be integers. Or, I'm taking the head of a list. All right, so you must be a list. Or, you're a procedure, so you need some input. Well, is there some input there? So, that's the kind of thing we do in, let me get this straight, static semantics. You want to say something there?
Yeah, well, I put this image up because it's, I think they are joking, right? So,
yes.
Yeah, so this is an example of sometimes even checking that, that the things you're adding up are all numbers isn't enough to produce a sensible outcome. And while this is just a fun joke from a cute little town in the States on their welcome sign, this really happens in real programs, right? And in particular, the software for Ariane 5 was put together by different teams, and they didn't agree on which units of measure they should use for distances. But they all just use a type of numbers, for distances, only they were communicating in completely different units. And Ariane 5 exploded seconds after it launched for exactly that reason. So fortunately, there were no humans involved. But that's the sort of thing where actually, how much can you validate that programs are in some way sensible, and that pressing the run button wouldn't be a bad idea, right? That's that business.
So I think, if my memory serves me correctly, that cost tens of millions of somethings, dollars, pounds, euros, tens of millions. And the problem was that at some point, some people added 7 feet to 3 meters. And because it only said 7 is a number and 3 is a number, the program thought, that's okay, we can add 7 and 3. But they didn't specify in the static semantics whether they should be using meters or feet. So that's the sort of thing, problems we can track. We don't need to run the program, we don't need to blow up our rockets, just on the machine in front of us, we can check that sort of thing doesn't happen. That's the value of static semantics.
I'm just finding the next bit. So the fourth thing we'll be looking at is, if I can only find my idiot cards, is compilation. Have I typed in the right URL? Yes, I have. Right, so you know, of course, that when you write a program in a high-level programming language, your computer's central processing unit does not understand that program. The CPU understands only the machine code of that particular computer. So something has to happen to your program in order to get it to work, in order to make the dynamic semantics of that programming language into an actual computational thing that happens on a box. And there are various ways to achieve that, but one of the ways that is most common and is most effective is compilation. That's to say, we literally translate the program from the language that it's been written in, the high-level language, into the machine code for the machine that we want to run it on. And we'll be having a look at how compilation happens. And indeed, we'll be building some compilers. I might show you one in a moment. So we'll be studying all the stages from syntax, how should a program go, dynamic semantics. Does this, is it a sensible idea to run this program, static semantics, to how do we actually make it go on a real computer? That's compilation. And one reason why we care about working with a high-level dynamic semantics for programming languages is to think about whether we've got the compiler right. I mean, think about how frustrating it is where you write a program, you know what the program is supposed to do, you've used the right constructs in your programming language to do that stuff, and then when you compile the program and run it, it doesn't work because there's a bug in the compiler. Right? This is, compiler bugs are extremely annoying and they're extremely expensive, and they cause great disappointment to ordinary programs who are just doing their job and doing it right. So, so compilers are things where you have to work at quite a high level of precision to get the details right. Because one for sure, you can't get away with like a compiler eating some source code and then kind of generating a bunch of machine code that it thinks is kind of sort of maybe the right thing, and then asking the programmer, is this what you meant? If not, I'll try again, right? The compiler cannot write programs in machine code using the same method of test and regret that some of us use when we're writing actual programs. The compiler has to do the right thing and mean it. Okay, so those are the four aspects of programming languages we'll be looking at, and we'll be looking at two programming languages in particular. This is your bit, Neil.
My bit. Right. Okay. So yeah. So like what we've said is that programming languages must do four things. They must have a defined syntax. They must tell you what value a program will give you once you run it. They tend to, because it's really, really important, do some static semantics to try and check if the program is actually going to give you that value. And then the most important, the sort of technical whiz of programming language definition of implementation is writing the compiler, which will turn the actual code into machine code you can run on the actual piece of hardware on your desk. So, four things. What we're going to do is exemplify that with two specific programming languages. Now, we could choose big, huge programming languages with lots of libraries and lots of features and all sorts of stuff that are out there in the world. But, they're just too big. Remember, what we're doing is we're teaching you the basic ideas so you know how to apply them into all sorts of different settings. So the two specific languages we're going to use are, one's called imp and one's called lamp. And we're going to exemplify those four features for imp and for lamp. Now, these are simple languages, and that's good because they're tractable. But they actually underpin all the basic ideas of all modern programming languages. Most of the ideas of all modern programming languages. And that's why I've chosen them. So imp, it stands for imperative. So this is what lies underneath Java, underneath C, underneath Pascal, underneath all sorts of programming languages, some which died even before you were born. I think the programming languages are old enough for that now?
Yeah.
Right, so this is in some sense the simplest, it's one of the simplest basic programming languages. It's only got three things in it. I think it's only got three things in it.
Pretty much.
It's got
Pretty much.
Pretty much. It's got assignment, x equals 0, that kind of stuff. It's got if expressions. If something's true, do this, else do that. So you can have choices. And it's got while loops, so you can do things over and over and over again. And that's all you need for a programming language. And later on in your course, you'll actually find that in fact, every single program you can ever write can be written using just those three things. That's how powerful an abstraction it is. Now, you don't want to write your programs in this simple language because it doesn't have all the nice comforting features that make writing things easy, but it has all the features you need to write every single program. So we're going to go through syntax, dynamic semantics, static semantics, and compilation for this language imp. And it was due to Sir Tony Hall, who's a British computer scientist that Connor and I have known quite well, I guess?
Yeah.
No, maybe not quite well, but
Yeah.
a bit.
He came up to me once and said, I knew your father, rather like a Second World War general talking to a Second World War private. So, a First World War general talking to a Second World War private. Yes.
So that's the first language we're going to use. Very simple, imperative. That basically, the word imperative, by the way, means imperative is like commands. In the English language, an imperative statement is a command. And that's what these things are. It's like the command is to set x to 0. The command is while this is true, doing something else. So it's all about commands. If you like, they're always about the state, and you're transforming the state. X starts off at 4, and you run your program, and x turns into 12. So that kind of programming language. So that's the first of our two programming languages. And the second programming language is it's called the lambda calculus, and that has, again, it's very simple, but very powerful. Again, it's so powerful, it can write every single program that you could possibly ever write. And it's got three things in. It's got variables, so very simple stuff. It's got what we call function application. So if you like, if you've got a program which requires some input, you can give it the input and then create a new program. That's function application. Or if you like, you know, you've got a method, you can give it some input. And then function abstraction, that's how you actually create the programs which require input. So, you know, if x is any number, let's do this to it. Or if x is any string, let's do this to it. Take a integer as input and then do this to it. That's what function abstraction is. So that's all you need, just those three things. So you'll have seen a bit about this. This is the sort of thing that underlies Haskell that you'll have seen in the second year.
Yeah. So I think Richard taught it last year, right? You're no strangers to at least the notation of the lambda calculus, and you can all do beta reduction. You'll be glad to know that the machinery we give you will do beta reduction for you, so you will never have to do it again.
By the way, it's worth saying, so Richard Connor taught this class last year. You may observe that neither Connor nor I are Richard Connor. And this will, if you've not observed that yet, this will become apparent in the way we talk about programming languages. You know, secretly between us, don't tell Richard. He's a little bit 1970s. No, given that this is 2010. No, I mean, Meg, I'm a bit out of date as well. Yeah. Anyway, so yeah, we will not be, you know, this is the sort of thing that some people used to sweat over. It's like learning Latin. You know, you do this and it's painful, it's good for you. We're not going to do it that way. We're going to show you how beautiful it is. Anyway, so these are the two programming languages that we're going to use as examples running through this course. And then at the end of it, we're going to say, oh well, I wonder what would happen if we started beefing these languages up. So what would happen if, for instance, we wanted to add exceptions in? So, you know, you've seen Java has exceptions, Haskell's got exceptions. You know, you say, well, let's try and do this. But if we detect an error, let's try and do that. That's what exceptions are. So we're going to take these languages and try and see what we do to add new features. So you'll know the answer already from the first part. We have to say, what's the syntax of the new features? Right, how do you write them down? What's the dynamic semantics of the features? How do you run these new features? What's the static semantics of these new features? How can we add extra information that we can check at compile time to it? How can we add extra information to make sure that our programs with these new features are going to work? And how do we compile them? So this will be like, you know, and by the time you're doing this, you'll be able to write your own language. So that, I mean, I don't know, you're all computer scientists, I hope you find that cool. I think it's cool that we can write our own languages.
Yeah, and I do it all the time. That's how I get stuff done. I mean, my dad gave me a very useful piece of advice when I was little. Well, he gave me several, but the one that's printable is never solve one problem. If you're asked to write a program to do a job, you might end up having to do lots more jobs that are quite a lot like it. And, you know, don't just pick any old programming language that's out there and start hacking. Think about what programming language would be really good for solving that kind of problem. And if that programming language isn't out there, make it. And then you've solved your customer's problem and also their next 700 problems. So programming languages are a really great tool for making a bunch of similar tasks easy to crack, right? When you have the power in your own hand to change the tools that you work with, right? Then you don't need to blame your tools anymore because you can make the good tools that you need to do a bunch of jobs. So in particular, one of the things that we're going to be doing in this class is building compilers. And compilers are, quite fiddly programs. They're quite difficult to write in ordinary programming languages. They're a bit of a nuisance in Haskell. They're a serious nuisance in Java. There's no way I would ever ask you to build programs as complex as compilers in a regular general purpose programming language, not in the course of one semester. So let me see if I can even find my mouse pointer. I can. That's not the language, that's from my previous lecture. What am I looking for? I'm looking for this file. Isn't it the font bigger? So this is the compiler for IMP. And yeah, so this is the shut up alarm. Yeah, so I'll just sort of flash this up as a teaser. Right? What I'm saying is that I'm practicing my own philosophy of taking compiler writing as a difficult, specialized thing to do, which could be made much easier if you had a domain-specific language specially adapted to the what makes compiler writing a tricky business. So I've built a programming language for writing compilers in, and we'll be able to use my program to interpret your compiler compiling one of your programs in some programming language that we've cooked up. So this is IMP, and basically I write down the grammar of IMP. So for example, let's find, here are the commands. Look, there's assignment, if, while, and various other bits and pieces. And then down the bottom of the file, I explain wherever, let me see where that's got to. This is the thing I'm looking for. Here's how to, this is a compiler for commands, which takes a command in a high-level language. So you can see we've got assignment here, and if here, and while there, and turns it into a bunch of funny-looking assembly language. You'll also be glad to learn that we're not going to be using you'll be sad to learn that we're not going to use a real assembly language for a real computer, just like I did in first year. I've invented a much simpler computer to target. This one's not called the tiny machine, this one's called the massive machine. And instead of having only 64 bits in it, it's got infinite amounts of memory. So we never have to figure out how to deal with out-of-memory errors. There won't be any. And each memory location can store arbitrarily large numbers. So we don't have to remember how to compute goddamn overflow, because there won't be any. And yeah, so the massive machine simplifies the process by meaning we don't have to deal with all sorts of annoying edge conditions and things that go wrong because computers are too small. It's only got 4 instructions, but the instructions are much more fun than the tiny machines are. So that's our compilation target, a really simple machine with a really simple assembly language. And we've got a domain-specific compiler writing programming language, which will hopefully let us get at the ideas behind compilation. Okay, we better stop there, Neil.
Yeah. How do we end lectures?
We collect in the 1-minute papers by placing a box at the door.